Hello everyone, my name is Rohit Singhal and we were discussing hydrocarbons. In the previous class, I have discussed about the conformations of the ethane or alkanes. In the previous class, I have discussed about the Sohor's projection, and in this class, we will discuss about the Newman projection and we will further proceed about that. So, let us start with it. Newman projection. What we have seen in the Sohor's projection was like that we have viewed the molecule along the molecular axis. This was the Sohor's projection, and what in the Newman projection is the molecule is viewed for example, how this Newman projection can be projected is there are two things, as we have seen the Sohor's projection of the ethane. So, what we have to do with Sohor's projection is like this, that we just have to compress one bond to another. So, that this CC bond molecular axis which I have shown the elongated version, that should not be there, and there should be two things, the front carbon, the carbon which is front or near to the eye is shown by a dot, for example this, and 3 hydrogen bonds are made at 120-degree angle. And the second thing is the rear carbon, means the carbon facing away from the eye is shown by a circle. So, these were the hydrogens, and let's show it with another color, and these are the hydrogens, 2 carbons. The hydrogens, these are shown at 120-degree angle. Okay. So, this is how the Newman projection is projected, means it is just the how we are viewing the molecule, that is how the different projections are. So, this also gives the two projections eclipsed and staggered, similar as the case of the Sohor's projection. This is one a staggered one, where the carbon hydrogen bonds are away from each other, and this one is the eclipsed. This one is eclipsed. Okay. So, two conformations we have seen, eclipsed and staggered. Eclipsed means the carbon hydrogen clouds are nearer to each other, staggered means they are away from each other. So, what is the energy barrier between them, how the strain takes place, let us discuss more about that. This one was eclipsed, this one is staggered. Between eclipsed and staggered, we know staggered is more stable, but they only have an energy barrier of around 12 to 13 kilojoule per mole, and this energy barrier and the molecule have always have enough thermal energy to overcome this barrier. Okay. So, that is the reason that these conformers can't be separated. Okay. So, was the thing that these two conformations, the eclipsed and the staggered, although they have energy barrier, but the energy barrier is very less, that is over around 12 to 13 kilojoule per mole, and the molecule at room temperature only has sufficient thermal energy to overcome that barrier. And that barrier so what happens when these molecules are at the room temperature, they contagiously shifting from one conformer to another. So, it is almost impossible to separate them as an individual conformer. So, conformers are those which are not separated at the room temperatures. Okay. As I have told now that staggered is more stable and eclipse is not. So, this comes a concept of toroidal strain. Whatever I have told that the staggered is more stable due to, more than the eclipsed because of the carbon hydrogen electron cloud. So, that is the same thing, the repulsion arising from the bond toroidal strain. Means the toroidal strain in the any molecule may be defined as the repulsion the molecule is experiences because of the two different electron clouds of the hydrogen of any two bonds. In this case, what we have discussed, what was there, that these hydrogens of two different things, these hydrogens, these are creating repulsions, and these repulsions is nothing but the toroidal strain. Wherever in the another case, in the staggered case, the repulsion is not much, the hydrogens are away from each other. So, toroidal strain is less here, toroidal strain is less. So, we can say that this toroidal strain in staggered conformation is less than the eclipse conformation. And if the staggered, if the toroidal strain is less, means the repulsion is less, means the staggered form more stable than the eclipsed. Okay. Or we can say staggered form or eclipsed form has more energy than staggered. Simple, those who which got more energy will be the less stable. Staggered. Okay. So, this was about the toroidal strain. Another concept arises due to this eclipsed and staggered conformation is the angle between the bonds. So, what the angle is, let us talk about that. Which angle I am talking about? Let's see. Okay. These two are two different conformations, eclipsed and staggered. Okay. So, there is an angle defined for this, there is an angle defined for such conformers. Let us take an example of the staggered conformation. We know this angle is 120 degree, right. this angle is 120 degree, and this bond is almost bisecting the angle. So, the angle between these two hydrogens, this angle is half of 120 degree, that is 60 degree. Whereas in this case, in the eclipse conformation, there is the bonds, the hydrogen CH bonds are almost parallelly aligned to each other. That means, the angle between those two hydrogens is almost 0 degree. So, in eclipse case, the dihedral angle is 0 degree, wherever in staggered conformation the dihedral angle is almost 60 degree, and this dihedral angle directly relates the stability or the torsional strain of the molecules. How it is? Dihedral angle is inversely proportional to the repulsion. What I am saying is, if the dihedral angle of the molecule will be higher, the repulsion will be less, and if the repulsion will be less, or I can directly say here also, and the is directly proportional to the stability. Okay. So, the dihedral, if the dihedral angle is more, the stability is more. Why? Because the repulsion, or we can say the torsional strain will be less. Okay. For example, let us take an higher case example. Let us not stick to. Let us discuss about this thing. Okay. And this is a propane, right. So, let us draw a conformation of this, and we will take these two bonds, these two carbons. So, what will happen? Let us say this carbon is this front carbon. Okay. This carbon is represented in the front. So, it has one hydrogen and one CH3, whereas the other carbon has 3 hydrogens only. Okay. So, in this case there are two dihedral angles there can be possible. The one angle is between H and H, this is 60 degree, the staggered form I have only formed, and if I consider this and H and hydrogen, it is almost 180 degree. And if I produce one CH3 here also. Okay. So, let us stick to it only. So, these are the things we can say about the dihedral angles, torsional strain. These 3-4 concepts are there. So, what dihedral angle are? So, dihedral angle is directly proportional to the stability, inversely proportional to the repulsions, torsional strain. Okay. So, yes, that is I have discussed till now the conformations. Okay. So, now we will proceed to the alkenes. We will discuss about their physical properties, their chemical properties, and how they look. I have already discussed about the isomers of it. I have already discussed about the nomenclature, the pi bond alkenes. How are they? Let us discuss about how their physical properties are. Okay. So, let us start with alkenes. Alkenes I have told. Okay. These are the alkenes. Alkenes have a loosely pi bond. Okay. Few properties we can say. Loosely pi electron, it is a electron rich species. Why? There is a pi bond in this. So, the electron cloud density is more comparable to the alkenes. That is why the alkenes are more electron rich, and these are loosely bound by a pi bond. Pi bond is not much stronger, not very much strong as compared to the sigma bond. So, the pi bond is loosely held because of the sideways overlap. Okay. So, these are the proper. Okay, so these are things. In the same case I have discussed about as I have discussed about the alkenes. Alkanes I have discussed about that fewer members, that the lower members of the chain are gases. Similarly, in the alkenes, the higher members C12 almost are liquids, and higher than that are solids. So, it is not much different than alkanes. It also has the same property that the lower members of the alkenes are liquids, are gases, then the liquids, and then it goes to the solids when the number of carbons increase a lot. And why it is so? Because of van der Waals force. And I have discussed van der Waals forces is directly proportional to number of carbons and it is inversely proportional to the. So, this goes same with alkenes also as alkanes. Okay. Solubility, if I discuss, I will discuss about the solubility of the alkenes. Like alkanes, not soluble in water because they are not polar, not soluble in water, although their polarity is slightly higher than the alkanes, but still not soluble, and we can say fairly soluble in benzene, toluene, etc. Okay. So, these are the properties. If I say the polarity, however, the alkanes have more polarity than alkanes, more polar than alkanes, as there is a C double bond, C bond. So, alkenes in general are more polar than the alkanes, but still they are not enough polar to be solubilized in the water or polar solvents. So, these are also soluble in the non-polar solvents such as benzene and toluene, as we have discussed about the alkanes also. Okay, so, in the next class we will discuss about the chemical properties of alkanes and also some how to synthesize these alkenes. So, that we will discuss in the next class. Thank you.